Another minor detail, right? Is the long word register, which we're fixing to set up and show you how to use. So we know, and you don't have access to these down here, and I'm not sure if the 1000 even has a floating point register in it. I'm not really sure, which would really mess you up when you get into your division, right? Understand? So, and what is the long register that we have available to us with 1100? We talked about that last class. Anybody remember? So we have two registers available to us that we can do math with right now. Is the book talks about the F register. So the F register uses it's all of the PLCs have this, by the way, but they don't call it floating point anymore. They call it real numbers, and that's probably what you learned it hopefully in math. Real numbers, right? So what's a real number? What's that? That's an absolute value of a number. What's a real number? So we have integers. What's an integer? But it has no fractions. So an integer has no fractions, right? A real number allows fractions, right? You understand that? So real numbers, and also real numbers will allow you to use what we call scientific notation. So we have floating point numbers, but the problem with floating point numbers, and I think I have the way these things are laid out. These things up to a certain number after you get it, it's just like your calculator. So in your calculator, when you're dealing with real numbers, your calculator has a range, right? You understand? Well, what if you exceed that range? What does your calculator automatically do? What does it automatically shift into? Scientific notation. And as soon as we shift into scientific notation, that means your numbers are rounded, right? You understand? So it means they're not as accurate. And this is the same thing true with the F register. The F register is a 32-bit number, but what they do is we don't sacrifice a bit for a sign. So bit 31 is the sign bit. It's not part of the number. It's the sign bit, right? You understand? So if it's a 1, it means the number is negative. If it's a 0, it means the number is positive. And then bits 23 through 30, this is going to be your what? The exponent, right? And then bits 0 through 23, it's going to be the base or the mantissa, right? That's the base of the number. Okay. So as long as you don't exceed this, then your exponent will be 0, right? You understand? And then after that, so this guy right here gives us extremely a large range. It gives us all the way up to a plus or minus, so it's still a signed number, but we can get up to 3.4028 times 10 to the 38th power using the floating point number, which is huge. But as soon as you start adding exponents, then the numbers are going to be rounded. Everybody understand that? But as long as we stay below this right here, then your numbers are going to be okay. But what if I've got any numbers that I expect to exceed the range, then we can use this, right? Y'all understand that? But if it shifts into scientific notation, then what do? We lose accuracy. That makes sense? Okay. Now, I don't know if I've got this on here or not, but I should. The MicroLogic 1000 supports what we call long words. And what's a long word? What's that? A word is 16 bits, so a long word is 32 bits, right? You understand? So your PLCs call them long words, but in computers we learn them as double words. So that means but it's assigned a number. It's not a floating point number. It's a signed number. So what that means, I get 2 to the 32nd. I get 2 to the 31st. So this is actually the range we have. Because we lose one of our bits for sign, right? So what we get a plus and minus 2 to the 31st. Well, not exactly. We lose on our plus. We lose 1, right? And why do we lose 1 on our plus? Because of 0. So that means if I can use long words, which the Allen Bradley, which the 1100 supports, then what that means, where's my calculator? I can have 2 to the 32nd. So where's my y to the x at? Right here, x to the y. 2 to the 32nd power. Oh, I'm sorry. Let's clear that. 2 to the 31st power, which would leave. That means we could have fine numbers up to that. So we could have up to a negative 2,100. I'm sorry, is that 2,147,483,248 negative numbers. 648 negative numbers and 647 positive numbers. Because your 0 takes up one of your positive slots, right? Everybody okay? Well, how do I set up long words? So when I go up to RS Logic, let me raise it up. So I'm going to load in a file that we call math. Oops. Docs. So what we do, of course, we have to do this offline. I'm going to come over here on my data file. So by default, we do not have an L file. We do not have an L data file. We have 0. We have a data file 0, which is output. We have data file 1, which is input. We have data file 2, which is status. We have data file 3, which is our B files or our binary files. We have data file 4, which is our timers. We have data file 5, which is our counters. We have a data file R, or 6, which is our control register, which we're going to use this semester. I have data file 7, which is our integers. I have data file 8, which are our floating numbers, our real numbers. And I need to add a data file L. What am I going to do? I've showed you how to do this 2-3 times. Come up here on data file, click what? Right click, type in what? Click on what? New. Then what are we going to add? We're going to add a long word. So there's long. It's going to automatically put it in 9, right? We can put it anywhere we want to, from 9 to 255. So if you want to skip over 9, that's fine. And we'll give it a name. So we'll call it L9. Follow the syntax of this goes. And then all of a sudden we have a long word file down there. Are we okay? Does this make sense? In fact, we should have, let's rename it. So let's see, rename. Yeah. So we'll call it long. Now we got L9. It did the L9 automatically. And then I'm going to call it long. So now what we have is we have this 32-bit signed number that we can use with our math, because it's very easy to exceed that range of integers, right? And in fact, I did it to start off with. Are you okay there? Now you can't do this on the 1000. Why can't you do it on the 1000? It's a fixed PLC. And the problem with fixed PLCs is you got what you got, right? Everybody understand? And what's the range? 2 to the 32nd. I'm sorry, 2 to the 31st, right? And then we have one more negative than we do positive. So we talk about operands. You're going to see this in the book all the time. And what's an operand? It's the part of the what? The instruction that actually specifies the number that we're manipulating. So these are so if you add two numbers together, the two numbers that you're adding together are operands, and your answer would be an operand, right? Understand? So these are the numbers that these instructions are literally dealing with. And there's the range for a long word right there. Oops, what's the matter? Got a mistake on my slide. What's the matter? Yeah, because I just copied and pasted. That's my fault. So I did it with my calculator, and I copied that in my calculator. So 2,147,483,647 plus numbers, and 2,147,483,648 negative numbers. But these are still integers, right? So the L is integer, and what is an integer? It's a signed number without a fraction, right? And so what's the absolute value of a number? Well, it can have, we could have an absolute value. We could have a fraction, but it don't have a sign. No, it doesn't have a real number. Absolute values have no sign. So they're all assumed positive. Yeah. Well, we're in math. I mean, this is, you got to understand this stuff because this is what? Everybody's okay on bits, nibbles, words, and all that kind of stuff. So I got it right here. This is not in the textbook, but what you got to do, guys, is when you get a PLC, if you get a name brand PLC, like either a Siemens or Allen Bradley's, they make all the documents free for you. Every document that they have out for these PLCs are free. And why? Because if they give away their documents, and an engineers can go back and see if that PLC does what they need to do, and it helps make a decision. So this is the instruction manual for the 1100 PLC, and it's available up on your student drive. So when you log in, if you ever go to My Computer, you've got a drive up there called, in fact, I think they're even actually on Blackboard. But Blackboard is usually real slow. So when you go to your drive, you'll have a drive over here called Students, which I don't have on this new computer, but it's going to be automatically mapped for you. Oops, sorry. I don't think this computer can find it. But you'll have it automatically mapped, and there's a drive out there called Students. It's got PLCs, and then all these manuals are actually available to you. So this shows us what we can do, where our operands can come from. And that's all this list down through here. So it can come from, so we're dealing with two things on our math, right? We're going to have a source A and a source B. We already talked about that, right? And source A would be your top number, source B would be your bottom number. But math, it doesn't make any difference. Subtraction, it would, because it would change your sign of your number, right? You understand that. Multiplication, it wouldn't make any difference. Division, it would definitely make a difference. So the quotient would be A, and the divisor would be would be B. And how do we get those operands in there? Well, they can come from any place that is specified here. So they could come from input ports. So we could bring them in. They could come from an output port. We're not actually accessing the output port. We're accessing the data table where this information is stored, right? Do y'all understand that? Okay. So what happens when your PLC scans, it puts it in these data files over here. So right now it shows me if I was to get my information from output 0.0, I would get all zeros in there. But it's an addressable data file, right? You understand? So what happens when your PLC scans the inputs, it updates these data files. And then when it runs your program, it'll update your output files, right? You understand? So, and of course, here's our input data file. So right now, my inputs are all 0. But I could actually take information from an input port, a 16-bit input port, and stick it into an add instruction. I could take something that I've stored in an output port and stick it into an add instruction if I needed to. So the information that we're adding and subtracting and multiplying, all those different types of things, where can they come from? Well, they can come, oh, I didn't want to do it. That's okay, I'll just go back to them. Yeah, they could come from an output, they could come from an input, they could come from the source file, they could come from the bit file, they could come from your timer accumulator, your timer preset, your counter accumulator, your counter preset. They could come from the control register, they can come from the integer register, they can come from the floating point register, they can come from the L, and we ain't got into this stuff right here, all these messages. They could come from your real-time clock, which we did talk about that. But all these we have access to. We can address directly, and we can bring these into a math instruction. These are the addressing modes available. We're not worried about indirect, but what's immediate addressing? What's immediate addressing? So addressing mode is how we get to operand. So this is another thing that you got to understand. This book will throw it out there in a minute, but they don't explain it. So I'm explaining some of these addressing modes. What's immediate addressing? We talked about that last class. The actual operand is specified in the instruction. So if I say add 10 and I put 10 up there, that's immediate addressing. This is the operand is part of the instruction. That's immediate addressing. Yeah, because that's the operand. So we would do, this would be constant. So constants are going to use immediate addressing. So the constant means that operand is part of the instruction. So we got two sources. What's the two sources on all our math instructions? We have source A and source B. Well, right here, notice, so on this slide right here, these are not the operands. So if I come up here and I said source A and I put 10 up there, then this right here would be immediate addressing. This is not immediate addressing because that is not the operand. That is the address of the operand. The instruction is giving you directions to where the operand's at. It's not in the instructions, it's giving you directions to where it is. So what addressing mode is being used right here? Well, this addressing mode is direct. So when we use direct addressing, it means what? We don't see the operand in the instruction because that is the address where the operand is at. So this says it's in data file N7 and it's in location in word 0. So this is going to be an integer, so that means we can represent numbers up to 32,000, right, plus or minus. And this is an integer register, and we're storing our answer in our integer register. Now what becomes the problem is we're going to have to be careful for our operands here, because what's the maximum numbers I could store in that in this integer register? 32,767 plus and 32,768 minus. So what happens if I try to put something bigger than, what if my operation comes up with something that's bigger than that? Well, no, something's going to happen. The PLC's something's going to happen. We're going to do that. So it'll give us an error, right? So how on the 1100s, how could I avoid that? Well, I could use an L register, right? An L9 over here, and that gets us all the way up to 2 billion, right? Or we can use a what? We can use a floating point. Now, what's the problem with floating points? Well, as long as we're below 2 to the 22nd, it's going to be using whole numbers. As soon as you go past that, it's going to automatically shift into what? Scientific notation. And as soon as it shifts into scientific notation, what does that mean? What does that mean? You've lost some accuracy on your answers. Because as soon as you shift into scientific notation, that means your calculator is rounding. It's rounding that last digit over there. Most calculators calculate 13 digits, but they only display 10-digit calculators. And why do they calculate those 13? So they can try to round more accurately, right? So yeah, you can get them out, by the way, if you subtract the whole number and then multiply by 1,000, you could pull the three numbers out of there. But so this is what we're going to have to be careful with, and this is something you're going to have to remember or know about your PLC when you use these add instructions and these subtract instructions. You're going to have to know the what? The range your answers are going to fall into. If they don't fall into your range, then you're going to have to go to either real numbers, right, you understand, or a higher designator register. Now, unfortunately, the only one we have above real numbers is the L register, which should get us in most situations, right? But still, the L register doesn't deal with fractions. And so if I'm going to deal with fractions, I got to make sure I use which register if I'm going to deal with fractions. Yeah, I got to use F8, right? Or F something. Y'all know that on the 1100, I can make more F registers. They just have to be what? Files 9 through 255. Everybody understand that? So here's add. We're using direct addressing. So before we started, we would have to come in and put something in registers, these two registers. Everybody okay? So what's being added? So if I was to take this and put a line right there, it's going to take this and add that to it. And then the line would be down here. And then this is where we're going to store the answer. So when you store the answer, you've always got to store the answer, right? Does that make sense? Yes or no? So this has got to be a what? This has got to use direct addressing. So what is the direct addressing? It means this is not the operand, this is the what? That's the address of where the operand is going to be stored at. That makes sense. So if you think about giving people directions, and that's what we're doing, we're giving the computer directions on what memory address to store or retrieve that information from. Everybody okay? And then we got two more we'll have to look at. We got one called indexed that's going to come into play, and we'll look at what we call indirect addressing. Right now, we've already used these, even though we didn't realize it, but the book don't define these addressing modes. But when you get into the data books, this is what they use. And why is understanding the data books more important than a book? Because odds are you might not be able to buy a book on the PLC that you have, right? You understand, but you should be able to get what? The data books or the instruction books for these things. In fact, when y'all take operation and programming in robotics, we don't have a book. Well, we make y'all use what? Anybody taking that class yet or taking it this semester? What do we make y'all use? The manuals that actually come with the robot. You know, aren't they fun? So this is the status register, but the problem is, when we get into counters and we get into timers, The status flags or the flag registers are actually part of the instruction. It has 3 word elements in there, which the book calls the registers, but it technically are not. One guy that this is when I actually look at the instruction manual that comes through. So this is that S register that we hadn't deal with, and we've only got one S register. So we got one input, right? You understand? For every 16-bit words, we have one input, right? You understand that? So we don't have to specify on our inputs. We don't have to specify. We don't have to specify out 0 : because as soon as I use an output instruction, it's understood to be data file 0, right? You understand? And when I do with my inputs, I don't have to specify the data file on my inputs, because the inputs are going to be there, right? You'll understand what I'm saying, yes or no? We've only got one status file, so even though it's 2, we've only got one status file, so we don't have to specify S2 if we want to address the status file. We just have to do S. So S, then I'd put colon, and then word. Are we okay? Kind of just like the inputs and outputs. So that timing register I showed you, the actual free running clock, is actually at S2 : 14, but all we have to do is say S2 : 14, because it's what? It's in the status register. So those 3 registers, you don't have to specify the file number on this PLC. Now, what I'm going to try to do later on this semester, we're going to play around with, y'all can't do it because we don't have it on any computers, but show y'all the variation between RSLogic 500 and RSLogic 5000. So RSLogic 500, these PLCs, the actual program manages the memory. On your 5000s and your Siemens, your S7s, you manage the memory. So when you bring these PLCs up, you don't have counters, you don't have timers. It actually assigns memory when you create them. Does that make sense? Which means it manages the memory more efficiently. So what I'm saying is that if I don't use any floating point numbers, then by George, I still, on RSLogic 500 machine, I am still losing all this space right here for floating point numbers, even if I don't use them, because the application is managing the memory, right? You understand? If I don't have any timers in my program, I still lose that memory, right? You understand? For 256 timers, that's three words of memory, 3 elements, 3 words of memory for every timer. So how much memory are we losing? We're losing 3 times 256, even if we don't use timers. So what they've done on your newer applications is there's no timer memory. The timer memory is only established if you put what? If you put a timer in your program. And then it allocates the memory for that one timer. It don't allocate the memory for 256. It allocates the memory for that one timer, right? You understand? So I'll try to show you all the difference with the Siemens PLCs and the. So what they've done away with is they've done away with the application managing the memory of the PLC. And of course, it makes it more efficient. So this guy supports immediate addressing, direct addressing, indexed addressing, which we're not talking about right now, but it does support it. Okay. And these are all addressed to, we can't address any map, cannot be addressed to the bit level. So we can't add 2 bits together. We got to either add a word or what? A long word. That's all we got available to us. So that's why we don't have to specify the word. If I wanted to get it for N70, I don't have to put a .0, right, to understand, because it's understood to be word 0. Everybody okay? Does that make sense? So this is the bit that was killing me right here that it don't talk about. So carry, what is the carry bit in the flag? In S0 S, word 0, bit 0, this would be the what? Carry. S0/1 or bit 1 would be the overflow, right? S0/2 would be indicate if we had an answer of 0. S0/3 would tell us whether it's what? A negative number or a positive number. Then S2/14 means we had what we call examine the state of the bits to determine the value of the results when the overflow occurs. So this actually shows us the value. And then this guy right here, we call it the overflow trap. This is S5/0. It actually traps an overflow and it'll hold it. Yeah. And so what's going to happen is this is going to cause a major fault on your PLC. And a major fault means what? Yeah, that big thing up here in the right hand. Somebody's already had it this semester. Oh, was this semester or last semester? Yeah, what's going to happen is this right here is going to turn red, and it's going to say I have a major fault. So I'm gonna force a major fault. Because some of y'all have seen it, some of y'all hadn't seen it. And so what I'm gonna do is I'm gonna come up here and switch this thing. Let's see. Yeah, I might have to do that. Okay, right off the bat, I got a fault. So this is a processor fault. And how can I get rid of it? How can I reset the fault? Very important thing to know too. Anybody know? So right now I'm dead in the water. Got a major fault. Processor stopped. I got this big little soft blinking red light up here on my PLC. Can y'all see it? See the little red light? Yeah. And it's labeled fault. How do I clear a fault? Try to clear a fault. What's that? Well, I get a new listing over here in my menu. I'm going to come up here on my menu, and now all of a sudden I have another listing that says what? Clear fault. It's, sorry. Yes, it does. It won't do it here. Well, we'll clear it. But what we do, if we wanted to see the actual fault, we would go into processor. I'm going to go to math, and it says I had a what? Can y'all see? Can y'all read it? I can't make that bigger, guys. I can't zoom in. It says S0/7, I had an overflow. So right now I got an overflow problem. No, this is a status register. This is a flag. I can't change the flags, right? You understand? Yeah. So that means I had an overflow. So what that means is I've tried to add two numbers that created something that was greater than what our signed numbers, and now the fault is down here. It's going to show me which it is. So my divide is giving me a major fault here. See, we're in the destination right here. Yeah. Now the problem is I'm using direct addressing, and I'm taking N7:0 and N7:1. So I'm taking N:0 and I'm dividing it by N7:1. So I'm gonna come over here and see what's going on with those registers, and they're both what? Now what's the problem with dividing by 0? Take your calculator and say 1 divided by 0. No, it's not going to give you a number. It's going to give you an error. A lot of people don't understand what division is. When we first got microprocessors out, microprocessors could do two math. They could add and they subtract. They could add and subtract. But adding and subtracting is the basis of all math. So I learned real fast what division what division actually is. Now, we learn multiplication tables, so we don't have to do true division. True division means you take that top number and you subtract that bottom number and you keep subtracting until it generates a borrow. And as soon as it generates the borrow, you count the number of times you were able to subtract, and that was your answer. Well, how many times can you subtract 0 from a number without generating a borrow? Forever, right? You understand? So any number divided by 0 is an infinite number. So that's why your calculator can't do infinity. So what does it tell you? Error. Well, look what I have in my divisor. What do I have for my divisor? 0. So you can't even subtract 0 from 0. Because if you subtract 0, if you divide 0 by 0, how many times can you subtract 0 from 0? An infinite number of times to generate. So any number divided by 0 is any number divided into 0 is 0, because as soon as you try to subtract the first time, you get a borrow, right? You understand? So we literally had to write programs to do divide. We had to write a program that did division. We had to write a program that did square roots. That was really cool. Trying to figure out how to do that when all you could do is what? Add and subtract. So when microprocessors first came out, they could do 2 math operations. What was that? Add and subtract. So if you wanted to do another math operation, you had to do what? You had to write a program. So what I need to do, what you're going to have to do, guys, when you load this up, is you're going to have to stick some numbers in here. You could say 1, and you could put what? Yeah. You can't do it in run, by the way. That's a good point. I thought y'all knew that, but you know, when you take for granted people know things, sometimes they don't. So if I want to change the contents of one of these registers that we have access to, I can come over here and I can double click on this. So I'm in the integer register and it brings it up. Right now I'm showing in decimal. We don't want to do it in binary because that would be very complicated, right? So I'm just going to double click on it when I'm offline, and then it lets me do what? Any number I want to. Yeah. So I'm just going to plug in ones. So y'all going to have to remember that, because we're going to, when we set up our program, our math program, this is what we're going to do. We're going to load the numbers in with a move instruction. But the problem is that if you don't do this, right off the bat, you're going to get a fault. You can clear the fault, then come into your integer register and put some numbers in there. Besides what? Besides 0, right? Yeah, when I first put the program in there and it faulted on me, I said, good gracious, I hadn't even loaded numbers in there yet. So notice right off the bat, it's got ones in there. I can switch it back to run. By the way, sometimes, especially when you recover an error, it's going to switch you to a remote program, right? And this has happened here. You're trying to figure out why it's not running because it's in remote program. It's not in remote run. So how do we get it into remote run? Just click on this, and now notice clear arrow is not up there. So the only time clear arrow is up there, yeah. I'm gonna click, yeah. Okay. And knows, and it didn't do what this time? It didn't fault. Everybody understand that? So if you get a fault, the first thing you probably need to do is try to clear it without doing anything. If you clear it and switch it back into run again, and it faults again, then you need to go in there and figure out what your fault is, right? That makes sense? And what you might have to do is you might have to get the manual out, because when you go, so where did I see the status register at? I went into what? Yeah, I went to processor, right? Status, and then I went to my math. Also, these are all your errors right here. So notice they're in here also. The math overflow should be in here too. So errors. But what they do is, since we have so many errors with our math, that they have a math tab. Are we okay? Yes or no? Math. but we've got to actually math, right? Are we okay? So we took care of that, and notice all that garbage is not down here in the destination anymore. But you don't get the error when you check it because it don't know what two operands you're going to add together. So now when the program runs, I can come up here and I can come up with any operand I want to. I'm sorry. This one don't let you change it. Dang it. So we might as well use. So right now I'm going to move. I'm going to move 35 into N70. I'm going to move 6 into N71. I'm sorry. I'm into N71. And what's N? What's N? Integers. Now my divide, I'm not using. I'm sorry. On my divide, I'm not using because divides can generate fractions, right? You understand that? So what register do we need to use on our divide? We need to use the what? The This is showing you a sample program where you can actually reset that while the program's running. So without even going to your status register, if you had a rung, reset the overflow. But we're doing a what? Can y'all see that? What instruction is that? Yeah, U inside the coil. What's the instruction is that? Some of y'all didn't get that far. No. So the overflow is latched, right? You understand? Now that's unlatched. So what they're actually doing is they're unlatching the overflow bit. So you could actually put this inside your program, right? You understand? If you had something happen every once in a while. So subtract. We have two operands: source A, source B. This is going to make a difference. So you're subtracting source B from source A. So you need to get these right because you could get the wrong sign on your answer, right? You understand that? That makes sense? And by the way, if you try to use constants or you try to use immediate addressing for both your operands, it's going to give you an error. Why? Why would you think that would be an error if you use immediate addressing for both your operands? It always has the same answer. There's no use of putting the math instruction if your sum is always 5, right? You understand that? So it will give you an error, and it would tell you have duplicates. So one of these have got to be in our cert. One of these have got to be direct address. So one of them's got to be a variable, right? You understand that? Yes or no? And then your destination has to be direct address because you got to store your answer in memory somewhere. Everybody understand that? So both A and B could both use direct addressing, right? Or one of them could use immediate addressing, one of them could use direct addressing. But the destination has got to be direct address. Everybody okay? And these are for all. How many instructions is this? So now it's easy. We're going to fly through this. Everybody okay now? Yes or no? We got a few people that's okay. So this is subtract. Go ahead. It's source B subtracting from source A. Now you can't change that, but you can change the numbers that you do it with, right? That makes sense. And what addressing mode is the book using? Yeah, that's direct addressing. So whatever's in integer register 0, we're going to subtract from that whatever's in integer register 1, and we're going to store it in integer register 2. Are we okay? Multiply. This is where we're going to have to really be careful about the numbers that we multiply because we could very easily exceed the range of our numbers, right? So we're going to take A, we're going to source A, we're going to multiply it by B. Source A and source B, one of them has to be a what? One of them has to be direct addressing. Both of them can be direct addressing. If not, one of them can be direct addressing and one of them could be a constant. And then we're going to have to do what? The destination has got to be the address of a data file. So normally with our math operations, even though we can put them anywhere, normally we can use the what? We can use the end register. We can not register, the end data file, which the book keeps calling them. Excuse me. We could use L and we could use F. But we could actually store. You could actually take the results of a math operation and store it into an output, into a 16-bit output word. And your outputs would take the state of the results of a math operation. Now, you could read stuff from an input, and you could add it, you could multiply that by something, right? You understand? And you could literally store this answer in an output port. And so your outputs would take the ones and zeros depending on what your answer was. Now that is neat. Up to the range, right? But remember, in fact, since y'all are going to be on the, by the time y'all get to the math, we'll move y'all over to a, I don't know, I might not get them over here today. Dang. I'm actually wiring some up over there. We don't have enough. So I think we got one beside me that's ready. And then we got one that Brianna's already on. And I think we got one across from y'all, James. The one, yeah. So right now I think we have, and then I could go ahead and move this one down there. I can go ahead and move this one down there. So that should give us 4, and I'll have 2 more that I'm going to wire up and bring over. So I'll take this one down there. That'll give us room for 8 people, which should be enough, right? We should need 4. And instead of using the N, let's go ahead and use the what register? L. The subtract. It's just like, in fact, most PLCs just cover all of these in a row because they're all the same, right? And hopefully we understand addition and subtraction. Multiplication, same thing. But what we're going to do is when you move over to your 1100, we're going to change this to the L register, and we'll be L9, right? And what are y'all going to name it? Long. Give you a chance to create another data file. Multiplication, we're going to be okay. We got to be real careful though. But 2 billion, and we're multiplying 16-bit numbers. We probably could. So the biggest. Divide. This is where we're really going to be. This is where we're really going to have to be touchy with the divide, because a lot of division is going to create a fraction. So what would happen if what would happen is it would truncate it or round it to a whole number, right? So what we're going to use here is we're going to use our F8 register for the division, and that way you can actually see fractions. Why we're going to use the long word? Because if we use a long word, it's still integers, and we'll lose our fraction. By the way, if you do use word operands, you don't actually lose the fraction. If you go into S14 and S13, S14 would actually be your quotient, and S13 would contain your whole number remainder. So even when you're dealing with integer numbers, you still don't, but you don't get a fraction, you get a whole number remainder, right? This is like when you first learned division. When you first learned division, you didn't use fractions. You put an R out there and put like a 3, a whole number remainder when y'all first got there. So what we're saying is you actually don't lose them. It'd be hard to deal with them, but these two status registers actually hold your what? Your whole number quotient, and also S13 would hold your whole number remainder, which is pretty cool. What do you mean? No, it's not source D divided by source A. It's source A divided by source D. So all you got to do is come up here, and here you'd put that line right there, and this is going to be your top number. That's going to be your bottom number. So it's always source A divided by source B. So we add it's source A added to it's source A added to source B, right? Source B. I should say that backward. Source and subtraction, it's source B subtracted from source A, right? You understand? So source B is always that bottom number. Right? Except on division, you'd put your line, instead of addition and multiplication, you'd put your line right here. On your division, you'd put your line right here. Right? So you're going to have to remember that. Huh? No, well, no, it's just that when you do fractions. So if I come up here and I say 6 divided by 8, that's the way we do fractions, right? You understand? And what does that say? Well, that says 6 divided by 8, and all I'm saying is that's just a way to keep up with which number goes where, right? Yeah. So this says 8 would be 6 would be divided by 8. Well, what we're going to do is say A is going to be divided by what? By B. And I was just trying to give you a little thing so you can remember where these operands come from. Huh? That makes sense? And on my add, what I would do is I would put my line. I would put my line right there, because this is A plus B, or I'm sorry, multiply. So this would be like your math. So this is the way you can keep up with it. Now multiplication, it don't make any difference what A is and what B is, right? You understand? Because 2 times 3 is 6, and 3 times 2 is 6. Where this is really going to come into play is not on your addition. Where's it going to come into play? Subtraction. Because this will determine your sign of your answer. So if you get these backwards, the sign of your answer would be wrong, right? You understand? So this makes division and subtraction where A and B is going to really make a difference. Because 6 plus 5 is 11, and 5 plus 6 is 11, right? You understand that? But 5 minus 6 is different than 6 minus 5. You get different answers. So when you deal with division and when you deal with subtraction, what you put in A and what you put in B is really going to make a difference, right? It's going to change if you got them wrong in your subtraction, it's going to change the sign of your answer. So if you're expecting a positive answer, you'll get a negative answer. If you're expecting a negative answer, you get a positive answer. And division is very critical, right? Because there's a lot of difference between 5 divided by 6 and 6 divided by 5, right? Yeah. So that's just the way I keep up with it. So on your regular math, we put the line here, right? Just like you would do it, and then on your divide, you'd put your line there like a fraction. So here's an example of a divide, except we're going to use an F8. Why are we going to use F8 instead of an L register down here, or even an N register? Because F8 are real numbers, which means they can have a fractional component. It only goes into scientific notation if you exceed the range, just like your calculator. Your calculator only goes into scientific notation when you exceed the what? When you exceed the range. And these are additional that we're just not going to have time to get into. Some of them we're going to talk about. Arc sine, so these are your trig functions. This actually allows you to raise up an x to a power. So that's instruction right there is really cool. So you can say like 10 to the third, right? You understand. This is your natural log, and this is your common log. Now, know the difference between natural log and common log? Natural logs try to do what things, normally things in nature don't vary on linear curves. They vary on a slope, like they vary like this. And that's why they're called natural logs, because we can calculate the way things vary in nature. And this is E, it's represented to E raised to some power. And E, I'm rounding this, guy, is like 2.73. And that's one of those numbers they came up with over time. Common logs, these are nothing but base 10. This is 10, this guy right here, and this is, so the common log of 10 would be 1. The common log of 100 would be what? 2. The common log of 1,000 would be 3. And then any number between that. So so if you had a common log of 3.5, you know it's somewhere between what, 1,000 and 10,000. And if we take, and by the way, this is called a bale. If we take that and multiply it by 10, we call it a decibel, which people call dB. Have you ever heard of dB? So 20 dB is actually 10 raised to the second. And what it does, it gives us the ability to round and still keep pretty accurate. So you ever heard of dB? It's just common. It's just not natural. It's just common logs. 10 raised to that power, and then we do what to it? Multiply it by what? 10. So 20 dB would be the same as 100. 10 to the second. You just shift the decimal point over, right? Huh? So 30 dB would be what? 1,000. Yeah, you got it now. So y'all got dB down already. This is probably one of the most powerful instructions we have available to us. It's called compute. And RS Logic 5000 supports one of these. Siemens S7 supports one of these instructions. What we do with this guy is, guys, is we stick the math equation in the actual box. So here's the actual equation right here. Here's the expression. So this is going to compute all this stuff, and it's going to store it in N7. So this is going to take the tangent of whatever's inside of N7. It's going to multiply it by the cosine of whatever's in N7-2, and it's going to store the answer in N7-0. So what's nice about this is you just put the what in there, the equation. So here we could do very complex math. So if I wanted to come up here and do all this stuff, we could still do it, but I would have to combine a lot of instructions to do complex math, right? Y'all understand that? So I could take the tangent up here in this rung, then I could take the cosine in this rung. I could multiply them the next together in another rung, right? And then, but what have I done? I'm using 3 rungs instead of just doing what? Instead of 1 rung. So what we actually do is we actually literally just do what? Put the equation. By the way, the asterisk, this has been true for years. We can't use X because X means other things in computers. So normally what we use is the asterisk indicates multiplication. So what we're going to do is we're going to take this guy right here. We're going to multiply it by that right there. And you'll see that used all the time. So let's see if we can do this equation right here. So A, we're going to multiply that by the natural log of B, and then why they're doing it here, I don't know. This is E, which is the natural log raised to the C power, and then we're going to add the tangent to that. So A is a variable. It's going to come from one of our data files. IN is the natural log, which is 2.73, 2.7. I say 3. That would be 2. I'm almost sure it's 2.73, guys. Then E raised to the C is the natural log too. But what they're trying to do is yeah, that's what E is raised to. So this would be the same thing right here. So what this would do, this would take the natural log of B, which would be E raised to the B power. But what they're trying to do, what they're trying to demonstrate is us using this instruction right here. So I know that 5000 supports this, and I know that F7 supports this, and that's the major PLCs that we've got in line. Now, the number of math equations that you get available to you is going to be determined by the PLC. These are just the math equations that RS Logix 500 supports. So if you went into the 1000, we need to pop one. I don't think this instruction is available to you. In fact, it'll be grayed out. I mean, I think the 1000s, you don't have any of your trig functions available to you. So the actual instructions that are available to you are actually determined by the model of PLC that you buy. And that's why when you, the first thing you do when you create a new program is select what? The CPU. And now your compiler knows what machine language programs to do, but it also knows what instructions that PLC supports, right? You understand? So that way you won't get a bunch of instructions that your PLC can't do. Normally on 500, they're still up there, but they'll be grayed out. Now, anytime you see something that's grayed out on Windows, what does that mean? You can't use it, right? You've seen that before? You hadn't? Really? A lot of your tab bars ago. So let's see if we can do this thing. So this is not an easy equation, but what they're trying to show you is they're trying to show you how you, instead of using multiple rungs, so all these instructions are available to us. Natural logs available to us, tangents are available to us, exponents are available to us. But instead of us having all these different rungs and letting this rung feed that rung, 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 we can combine everything into one equation. So what we do is we set up some assigned registers. So A, we're going to use F8. B, we're going to use F8. So we're going to use F8 for all these. Because why? We're going to probably be dealing with real numbers, right? And we're going to use a normally open contact to start the thing. And we're going to place it into, we're going to place our answer into F8-4. So here's the math equation. So what we did is, this is just what I assign. That's what you assign. So you got, if you're going to deal with variables, you've got to pull them out of data files, right? Okay, you understand. So we're using all direct addressing. Okay, this makes sense. So this would be up to you. So the first thing what we're going to do is we're going to use this X to, we're going to create a 2.718, which is the natural log. Some reason I had 2.73 in my head, but I guess it is 2.718. And then then we're going to take the natural log of that and we're going to put it in where? I'm sorry, we're going to raise it. Yeah, then we're going to put it in what? F8. So here's the equation. So we're going to take F80, then we're telling our PLC to take the natural log on that. Then we're going to take F81. Where did I get F81 from? What's F81? This is B. This is source B. Okay. What? Excuse me? So this is B. So B is, anytime I see F, so our equation is what? Here's the equation right here. I'm sorry, it's up here. So anytime I see B, I'm going to use F8:1. That makes sense? Anytime I see A, I'm going to use what? F8 colon 0. Anytime I see D, I'm going to use what? Are we through? I'll use F8 colon 3. Okay. So here it says natural log, and what are we supposed to do? We're going to take the natural log of B. This says A, so anytime I see A in my equation, I've assigned these addresses. So there's A. So over here, there's A. Okay, so that takes care of that one, right? This takes the natural log of F8 colon 1. That takes care of that one. Here we're taking F5, which is what we're doing up here. So here we're using y to the x. So we're using 2.718 raised to this power right here, which would be the C power. So I'm using F8 colon 2, right? And then I'm taking the tangent of F8 colon 3, which would be the tangent of D. And where am I putting my answer at? Yeah. So this is kind of unusual. Now, what do you get this? I don't know. But what you need to understand is that this guy right here, instead of me, if I've got to do a lot of math, and I'm doing the same math all the time, and I'm taking the answer from this one and feeding it into this one, the answer for that one, feeding it into this one, taking the answer for that and feeding it into this one, I could actually come up with the equation and do what? Put it in a compute instruction. Y'all understand what I said? So I say add this register to this register, stored in the destination. Take this destination that I stored the answer in, use that as one of my operands down here, and do a subtraction with it. Take that answer and store it into it and use that. So what you've got is you've got all these rungs. So I could do this, guys. I could do this with one, two. I could do this with 4 rungs, or I could do it with what? One rung using a compute. So what we do with a compute, what does the compute allow us to do? It allows us, instead of doing addition, subtraction, multiplication, and division, we just put our what in there. We put our formula in there. And it'll do it with how many rungs? 1 rung. A really powerful instruction for math. I mean, you might get into some PLC programs where they don't need math. I mean, we have a lot of PLCs that PLC programs that do what you learned in motor controls. How many of your circuits in motor controls did math? And that's the problem. So what we've got is that RS Logic 500 goes ahead and keeps up all these. It assigns all these memories, and we might not ever need them, right? You understand that? So what did y'all use in What did y'all use in motor controls? You used what? Relays, right? And timers and count. You didn't even use counters. All you did was timers, because counters, we actually have an electronic circuit that does counting. So we can't count with relays. But once we get into PLCs, not only do we have the advantage of programming all that relay logic in there, but this is the advantage of a PLC right here. A PLC can do what? It can do math. It can count. It can do math, right? It can do sequencers. It can do shift registers. We can do a sequencer with relay logic. We'll show you. I think we got a sequencer over here. Sequencers are really, really cool. But of course, I say that a lot, don't I? I don't even know if that's the expression people use now. So what do y'all say now for when something's really neat? These are some other instructions. So we get to go to the lab. Clear. What does clear do? Well, what is it going to do for us? Yeah, and this book does not do this right. Clear does not clear a register. It clears a data file. It puts the zeros in the data file. So I'll show y'all. So what we do, and a lot of times when you reset a system, if you set your system up right, and this is the way the Festo line is set up, is that when you reset it, you want all your outputs to go to 0. Well, how do they make all the outputs go to 0? Well, they just clear out that data file. They just clear out the outputs. So we use this a lot. This double divide, this is only available on the RS Logic 1000s. We don't need it on the 1100s because we have that long data word. So MicroLogic 1000s has this double divide by, and what this does, it allows us to double divide by it allows us to divide by 32-bit data, but that's not exactly right too. One of them's got to be 16 bits. So I think what you're dividing by can be a maximum of 16 bits, and what you're dividing into can be a maximum of 32 bits. And then if you use an integer file, it's going to round it out. But if you, what's this S13 and S14? You remember that? So how you spell quotient? Q-U-E-N-T or something like that. So S13 would if you need the remainder, S13 would have the quotient, and S14 would have the remainder. It's going to be. What is DTD going to do for us? Yeah. So what would happen is we have bits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And I run out of space. So let's say I came over here and I had 14. That would be a 4-bit number. And what would happen is all these bits right here would be set to 0. And the bit and 14 would be set to a 1. So what it does, it actually tells you, if I came over here and did this, what's that, a 10? Then bit 10 would be, that would be an 8, I'm sorry. So 8 would be set to 1. This would be a 10, so this would be a 10, so 10 would be set to what? 1. So what it does, it decodes the bits for you. So it gives you a bit that indicates what the 4-bit number is. So if you had a 15, then bit 15 would be a 1, which I don't have down there. If this was a 3, then bit 3 would be a 1, and all the rest of them would be what? 0. Now where you'd use that at? We use this sometimes to sequence through, like we got a counter, and we want the outputs to sequence through 0, 1, 2, 3, 4, 5 like that. Then you would actually store this in your output register. What does negate do? Negative. What does this do? So this would make a what? A negative number positive would make a positive number negative. Yeah. TOD. This is pretty interesting. What does it do? Yeah, BCD. And what does FRD do? Now, why would we need this, guys? So you'll run into these often. Why would we need those? Because what number system do you understand? Decimal. What number system does the computer understand? Binary. So that means I might have some buttons on there that I'm going to try to set the speed of a motor. And I come over here and I enter 200. That's going to be 200 decimal. we could read this into our PLC, then we can convert it to binary, and now we could process it, right? You understand? Now I want to display numbers to you. I want to display the speed of the motor. You don't understand hex, right? You don't understand binary. But what we could do is we could take the speed and do what? Send it through which instruction? That instruction, and then send that out. So what we do is we display decimal numbers, right? You understand? Even it gives us the ability to the PLC to convert from binary to decimal, and I'm sorry, from binary to BCD or BCD to binary, so it can communicate with who? You. With you, not the machine. Machine don't care. It's you that wants everything to be in what? Decimal. So I can come up here on a dial and I can enter decimal numbers, and we can bring this into the PLC. The PLC then I'd bring it in. I would run it through this instruction right there, and it would convert it into what? Binary. Then what can we do? Then we can do math on it. We can do all this other kind of stuff, right? You understand? And then I want to display you the answer. Well, the problem is I don't understand binary. So we could run it through this instruction, and what would it do? It would convert it back to BCD, so we could display decimal digits. And then SQR, what's SQR? So this allows the PLC to communicate numbers to me, right? You understand that? So I can enter decimal numbers into it. It can automatically convert it to binary and do what? And it can do math with it. We can do all this kind of stuff with it. What can we do? We can convert it back to decimal so we can display information. So these are all considered math instructions, guys. And then of course square roots. What does square root do? Take the square root of a number. Here you definitely need to store this answer. So that's all the math instructions that this book talks about. How many are supported by the 1,000? Every one of these is supported by the 1,100s. I'm not sure what are supported by the 1,000. But how can you tell? Just go to your math instructions and see which ones are grayed out and which ones are not. Right? And I'm surprised y'all hadn't heard that term grayed out before. Let's see if we got any. Yeah, so that one's grayed out, that one's grayed out, that one's not, that one's not. That's the ones you don't have. This one, so RS Logic 500 supports them, but this PLC don't. Okay, so they don't have the math circuitry of the application. So that's what we mean by grayed out. So here's our math instructions. So the only thing this one guide doesn't support is that CPT instruction. So I cannot do that one last one we went through with this PLC. So the next instructions, we're fixing to go to lab. Let's just take a break and go to lab. Next instructions we're going to get into compare instructions. This is the next thing that's in your book. It's got compare. I think it's got jumps, which is really cool. It's got some more move instructions. What else is in that chapter? I'll look at it real quick. Subroutines are in here. Yeah. Bit shifts, data. This is a pretty. The next chapter is a pretty easy chapter. This one will go in next one we go into. I think our next test is when? Our first test.